Well, a warm welcome to anyone joining. Thank you for being here. Go ahead and get yourself ready with a notebook. Grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have part 2 of using the IVT for any of you students in AP Calculus or even Calc 1. If you haven't checked out the part 1 video with some of the easier problems and a brief overview of the IVT, a little bit about how it works and how we use it, if you missed that, I'll put a video link in the description. You can go check it out. Part 1 is pretty useful. In this part 2, we're going to be dealing with using the IVT when you don't have an explicit function given, like a polynomial or a trig function, a quadratic, something like that. We just have to use the fundamental principles of the IVT, which is a function that is continuous, takes on all intermediate values between f of a and f of b on the interval from a to b. That was pretty well said, if I do say so myself, so make sure you understand it in that precise way. You can see 3 problems here. Might be kind of tough to see them, so let me give you a closer glance of them. We have first a multiple choice problem with a chart and a missing function value at k. We have another chart, but it has f of x and g of x, and we're asked the function h of x, f of g of x minus 6. We have to use the IVT there. And then this third one, kind of tougher, we're asked about the rate of change. And I got a little bit lazy. There's not really any context there. It could have been like the number of people in line or something like that, but I just didn't feel like adding any flair to that one for some reason. Either way, we have to use the IVT. Go ahead and give yourself about 6 or 7 minutes. It shouldn't take much more than that. The middle one will take longer, but it should really only take about 6 or 7 minutes to solve these problems using the IVT. And when you're ready, I'll pause the video. You can come back, see how we did it here. Alright, let's get started. So, in the first one, we're given a function with a missing function value, and we're told that the function is continuous on 0, 2. So that means the IVT should apply from 0, 2. The question is, if the equation f of x equals 1/2 must have a solution, 2 solutions in the interval, what does k have to be from these options? So a really great way to do this quickly is to plot these points. I know that doesn't sound very quick, but just to really solidify your understanding, I think the graph would definitely be helpful. So those are the 2 points that we know of. So just from those 2 points alone, we are not guaranteed to pass through 1/2, which would be like right there, right in between 0 and 1. It's not guaranteed that we would pass through there. So we need to fix this value of k, which is somewhere on the x equals 1 spot. I'm going to put it there for now, but it's so that I can move it. It's somewhere at x equals 1. See how if we dip lower beneath it, that could help us out. Right? That could definitely help us out. So let's try these options. If a equals 0, if a equals 0, I see that the function has to connect and cross the line between 0 and 1, and it has to connect and cross the line between 1 and 2. So that looks like the best choice so far. B says 1/2. If I move this thing exactly on the 1/2, I only need to cross once. So that one only have one solution for f of x equals 1/2. And of course, if I have the y values any higher than that, especially up at 3, I think it's clear that this would not have to cross twice. So really, we're trying to find what value of k would force the graph to cross the 1/2 line twice. And we don't know where it would happen. We don't know if it would like be right at the end, or if it would be like right at the beginning. We don't know if it would cross more than once. It could. It could cross 3, 4 times. But we're guaranteed it will have at least 2 solutions if we make it cross once, and then if we make it cross back. Pretty simple. Okay, let's look at the second problem. I do want to provide a disclaimer that I really don't see the intermediate value theorem tested much on the AP exam. You might get one or two questions that regard it, but you're definitely going to have some IVT questions on your first test, so that's part of why we do this. Let's take a look at the second problem. We have a table for f values and a table for g values. We want to look at the function h of x equals f of g of x minus 6. We want to prove that there must be some value such that h of r equals negative 5. Sorry if you can't see that. That is a negative 5. So what we're going to have to do, since it's continuous, is we're simply going to have to find the endpoints. H of 1, which is going to be f of g of 1, and then minus 6. Well, if we look at the table, we can find that g of 1 is just 2. So we're really doing f of 2 minus 6, and then if we go look at the chart, f of 2 is 9. So this will be 9 minus 6, or 3. That's one of the endpoints. Now if we plug in 5, we do the same process, but, if we plug in 3, we don't have any function values for x equals 5. F of g of 3 minus 6, which is going to be f of, let's take a look at the chart, g of 3 is 4. So we're going to replace the g of 3 with the 4. And then we go back and look at f of 4, and we see that that's a negative 1. So this is going to be negative 1, oops, why did I write a 4? Negative 1 minus 6, which is negative 7. Okay, and that is the other endpoint. Now since negative 5 is in between h of 3 and h of 1, and h of x is continuous, because it's continuous, by the IVT, h of r, I guess I should say h of r is continuous. I mean, we used x on the chart, but it doesn't matter. H of r equals negative 5 has a solution. I'm not saying it only has one. That's the tricky math people think. I'm saying it has a solution for sure. I'm not going to speak on whether it might have 2, it might have 3, it might have 4. There's no need to say that. We can just say with confidence that it has a solution on the interval from 1 to 3. Okay, great. Let's move on to the last problem. So the last problem is something that you could possibly see as like a part A on a free response question on the AP exam. So n is a differentiable function, which means that the derivative is continuous. Since the IVT requires continuity, we're going to be able to use the IVT on n prime, on the derivative. And there is another theorem which you'll learn about slopes called the mean value theorem. That one's a little bit more specific. Yeah, that one's a little different. This is using the IVT on the derivative. All right, so let's take a look. How can we figure this out? We want to prove that the rate of change, which is kind of like the slope, I want to prove that the slope must happen 22 at least once on the interval. So what we're going to do is we're going to find all of these average slopes on these intervals, like 0 to 2, 2 to 4. We don't technically need all of these intervals, but I think it's good practice computationally for you to be able to do these average slopes. So let's find the average slope from 0 to 2. It's going to be rise over run. So y2 minus y1 over x2 minus x1. That's 40 over 2, or 20. Pretty easy. Next we have 45 minus 75. So the slope is negative now, over 4 minus 2, which is negative 15. That's negative 30 divided by 2. And then we have 5 minus 45 over 6 minus 4. So we'll have negative 20 because it's negative 40 over 2. And lastly, we have 55 minus 5 over 8 minus 6, which is 25 because that's 50 over 2. Now, how does this help us? There is something called the mean value theorem, which you haven't learned yet, but it says that on this interval, the slope had to have equaled 20 at some point. So we'll say n prime of t equals 20, somewhere on the interval from 0 to 2. But then later on, the slope goes negative, that's great, but then later on, the slope goes to 25 at some point on the interval from 6 to 8. So therefore, because 22 is in between 20 and 25, we know that the derivative, which is the slope, had to be 22 at some point. We say for some t on the interval from 0 to 8. I'm not going to get super specific about the intervals, so I just want to be careful and say somewhere from 0 to 8. We could kind of refine it and figure out when that happened. For example, we can determine that it definitely happened somewhere between 4 to 8. But we know for sure it happened somewhere from 0 to 8, just from the IVT. Okay, so that last problem allows you to realize that you can kind of play with your starting point. You can play with your intervals to see where you need to shorten it to use the IVT. Also, in the first problem, one way to solve this is to make sure that we have two solutions, meaning this would have to be above and below 1/2, and this would have to be above and below 1/2. So you could do the IVT like twice. I chose to go with the graph representation for that problem. Okay, I think that's enough blab out of me. I'll see you guys next time.